The effect size is intended to provide a measurement of the absolute magnitude of an effect independent of the size of the sample. As we talked about before, a large sample size can go a long way toward delivering statistical significance, like the 256 and the 144 sample sizes that we saw before. However, I would like to have some other indicant of practical effect. How strong was this in a general sense? And the formula could not be more direct. It's just the treatment minus no treatment over the standard deviation. In fact, let me even simplify that. The mean difference over the standard deviation from the population. And what we mean by mean difference is capital M minus mu. And let me walk through this. The standard deviation is included in the calculation to standardize the size of the mean difference, much the same way that z-scores standardize locations in a distribution. For example, a 15-point mean difference can be relatively large treatment effect or a relatively small effect, depending on the size of the standard deviation. This phenomenon is demonstrated in figure 8.9. The top of the figure shows the results of a treatment that produces a 15-point mean difference in SAT scores before treatment. The average SAT score is 500, and after treatment, it's 515. So how big of an effect is that? Well, it's 15 over the standard deviation of 100, as it says right here, which is kind of a tepid effect. Now, what do we do with that? Well, let's visit that here in a second. Let's actually get to what we might mean by a Cohen's d, what to do with that. But let me express the formula literally, if you don't mind. For example, do you remember the problem that had 256 participants that had to do with the sedative? We enjoyed statistical significance by an eyelash. You see the green barely exceeded into the critical region. So we had that. Did that help reject the null hypothesis? Yes. Was there a strong effect size? Here's the literal rendering of the formula. Cohen's d is capital M for the sample mean minus mu, the population mean, over the population standard deviation. From that problem, the sample mean was 1440, the population mean was 1500, and the standard deviation was 400. And what I would get here if I actually did the math is 0.15 negative, but we ignored negatives, or I'm just going to have you ignore negatives. In fact, I'm double checking my math. Yep, got it. So the absolute value of that effect size would be 0.15, and I tend to focus on absolute values. So the suggestion is not really. Now you can see how basic that formula is. It's peanuts. It's nothing. Just capital M minus mu divided by the population standard deviation, not the standard error this time. It's a different thing. And I can get this number 0.15. Did that have a really strong effect size? No, not particularly. 0.15 is not considered to be a very strong effect. Now, how do I know that? Well, there are conventions on this. Let me get to that. This is from roughly 264 in the text. I forgot the page number. But when I evaluate effect sizes with Cohen's d, anything in the neighborhood of 0.2 is considered small. 0.5 is medium and 0.8 is large. And by the way, it could be a lot larger than 0.8. It could be 2. It could be 3. It could be huge. But this is sort of a rough guideline that ironically Cohen didn't sign off on himself. He never wrote these guidelines. Someone else came along after his death and assigned these effect sizes. But the notion is I could have statistical significance and a rather tepid or weak effect size. And what drove the statistical significance in that case was the huge population size. I could have a smallish effect that sort of put me over the threshold for statistical significance. So here's a question. Can we have statistical significance rejecting the null hypothesis without a strong effect size? Yes. Absolutely, especially when n is high, like 256. I could have a rather token effect, and in this case, what was that token effect? Just a difference of 60 saccades, which isn't that much, and enjoy statistical significance because the sample size was large. However, in terms of everyday terms, it really wasn't that large of an effect, and Cohen's d tells me that. Can we have statistical significance rejecting the null hypothesis without a strong effect size? Yes, especially when n is high, like 256. So, and again, here are these rough guidelines. And it's ironic that Cohen would have thought this was abusive. He just died in 01. Nope, excuse me, 98. Died in 1998. And sure enough, that effect size being in the neighborhood of 0.2 is smallish, so not terribly impressive. I'll tell you, if we were taking this class 30 years ago in the spring of 1990, it might have been the case that Cohen's d wasn't even mentioned. Cohen's d is a relatively recent advent into statistics textbooks. It used to be the case that we just weighed in on statistical significance without much comment on practical significance. This Cohen's d is a separate comment because, again, it completely avoids any influence by sample size. When sample size gets in there, it can be infected by that. Cohen's d has a way, as you can see by the rendering of the formula, it doesn't take that into account, and therefore we can get a somewhat of a different picture of the practical effect, and that practical effect is listed informally in this table here. Cohen is hugely influential. He just died in 1998, I want to say, and he wrote a few books towards the end of his career, just I think 2 books actually, that proved to be just ginormously influential, just huge, and making us reconsider some of the foibles and fallacies of one sample hypothesis testing, including making it near necessary that we always have a separate comment on effect size in addition to statistical significance.